Hey guys, and welcome to a long overdue Advanced C++ and Graphics tutorial. Today we're going to be just going over a small game I made that's going to help us in the next tutorial when we want to go over spatial partitioning. Today we're just going to be kind of going over the code for this, and I'm going to show you something called macros. You're probably already familiar with macros, but I'm also going to show you Variadic arguments for macros, which you may not be familiar with. And all of this is going to, of course, set us up for our spatial partitioning episode for the next video. And the reason I made a brand new game for this rather than using the zombie game is because the zombie game's code wasn't really designed from the ground up for spatial partitioning, and we would just waste a lot of time kind of hacking it in. I did implement it in the zombie game, and I will give you guys that download in the next tutorial, but today we're just going to be going over this BallGame that I made because it's going to be a really useful tool for teaching you guys spatial partitioning. And right off the bat, I want to bring your attention to the warnings down here. Whenever you build your game, you get errors and warnings. Now, until now, we've been completely ignoring warnings, which we should not have been doing. One of the most common warnings you're going to get is this warning signed-unsigned mismatch. We should go ahead and stifle all these warnings. We should fix them because there's often a lot of there's a lot of bugs that can be prevented by looking at these warnings. So this signed unsigned mismatch, this happens whenever you have a signed integer like this int I and you're comparing it to an unsigned integer. If you mouse over the size function, you'll see it returns this weird size type variable, and that's an unsigned int. Now we could fix that by saying unsigned int here, and that's mostly correct unless for some reason vector is returning a size that is not 32 bits. You could also do size t. That's a common one. Size t. That will be probably correct. You're not going to get the warning with this, but they might be different sizes. For instance, this might return a 64-bit and this might be a 32-bit. To get the perfect variable that will always be matched up correctly, you can just use the auto keyword. And that will select the variable that is, or the type that is the exact same type that gets returned by this dot size, and that will stop that warning. Now, another warning you're probably going to get a lot is something like converting integer to float or something like this. For instance, if I get rid of this float right here, this event.button.x is a signed integer, but we're passing it in as a float. That's going to give us a warning because it thinks we don't know what we're doing. To just tell it that you know what the hell you're doing, you just say float here. You just cast it explicitly to a float, and that will shut up the compiler, and it will believe you that you know what you're doing. Okay, so let's go ahead and run the game, and I'll go ahead and show you what I've made. It's a pretty fun little game. Not even really a game, it's just a toy. So here we have the ball game. Now we have various sized balls, and they have different colors, they have different masses. They do just simple 2D elastic collisions with each other, taking into account momentum, and they bounce off the walls, so they are confined to the window dimensions. You can click on a ball and drag it around and slam it around and make a big mess, and when you release it, it'll fly in that direction. And that's pretty much it. Of course, I can also change gravity. If I use the arrow keys, I can press left, and all of the gravity goes left. If I press right, it all goes right, down goes down, up goes up. So I have full control over 4 directions of gravity, and then I can disable gravity by pressing spacebar again, and then they'll be free to move around. And as you can see, they can kind of clump up here. This might be a bug you guys can look into. I didn't spend a whole lot of time on this game, so I'm sure you guys can mess around with it if you feel like you want to spend the time to do that. And there's another bug. Let me see if I can get it to happen. Take a look at this this red circle that I'm holding onto at the top here. Watch what happens when a white ball, okay, just like that. If you see, sometimes when a white ball hits it, it'll kind of slide around it instead of like that. You can barely see it. These are like sliding around in a circle like they're attracted to it. That is definitely a bug in my code. So if you guys want to try to fix that, that would be a cool exercise. If you fix it, definitely put a comment in the description saying how you fixed it. What I also want to go over today is some of the architecture of this. This isn't what we usually do. If I go to ball.h, this is our ball struct. You'll notice I have this POD at the top. That stands for plain old data. Now, something that is plain old data is basically just a struct. It has no functions except maybe a constructor, which this is a constructor right here, and everything is just data. And you'll notice these are all public variables because remember, a struct is public by default. Now, you're probably asking, well, why don't we use getters and setters? Why are we making this public? Well, whenever you have something like this that's plain old data, like for instance, our ball is just a collection of variables, usually it's safe to just make everything public and to just trust the programmer that they know what they're doing. Not to mention, these variables are probably going to be accessed and set outside of their class all the time, so writing a bunch of getters and setters would just be a waste of time. I know I've drilled into you guys that you should be using getters and setters, but you don't necessarily always have to use getters and setters. In this case, for this specific architecture, which is similar to kind of what the entity component system architecture is trying to accomplish, which we will be learning later, this is a way to just sort of decouple all the different components of your game, like rendering and the logic controller and the data. So I want to tell you guys about something that is called the single responsibility principle, SRP, single responsibility principle. This is a principle that basically says each class should have one single responsibility. You should be able to describe what it does in a single sentence. So for instance, this ball, we can say it is the data for a ball. That's really simple. Now I've also made another class called the ball controller, and we could say this implements the logic for balls. It controls balls. And I also made another thing called ball renderer, and this we can say it renders the balls. Notice how everything gets its own file, everything's cleanly separated. Now before, in our previous tutorials, we would always put the draw functions and the update functions inside the ball. A ball would be a class instead of data. And that's okay, it's not terribly bad. However, anytime we want to, say, make a brand new renderer, some different render functions that will render a ball differently, we're going to have to toss it in this class. And this class is going to get bigger and bigger, and there's going to be coupling between the functions. We might accidentally mess up a function we didn't want to touch. However, with this, if we wanted to make a new way to render a ball, maybe we wanted to render a ball with like some cool lighting, instead of messing around in ball renderer here, we could make a brand new ball renderer. We could have a lighting ball renderer, we could have a reflection ball renderer, whatever. We could have all these different renderers, and we can just pick which renderer we use to render the ball. This is called decoupling the data from, or the logic from the rendering and the data from the rendering. When we decouple things, when we separate things like this, it makes bugs a lot easier to track down, it makes the code a lot easier to manage, and it lets you get a lot more flexibility in what you do. For instance, we have this basic ball controller here, but maybe we wanted to have a different set of logic that we could switch between. Rather than making this ball controller bigger and adding a bunch of code to it, making a huge mess, we could make a whole nother ball controller class. We could call it Super Ball Controller or something that does something different, and we could use that to update the balls. So yeah, as you can see here, this is the ball controller. It updates the balls. It takes some events here. We have on mouse down, on mouse up, on mouse move, and I pass those in maingame.cpp. If you go to maingame.cpp, you'll see all this stuff. It looks really familiar. It's pretty much almost the same as we had in our zombie game. It's a little simpler though. Other than the init balls function, we have this process input function that we had before, and on some of the events we will pass those events on to the ball controller so that it can handle clicking and dragging the balls. And then we also have some gravity stuff here, of course. So you guys can look through all this and figure out how it works. I'll go real quick to ballcontroller.cpp. This update balls function is where all the balls get updated. It gets called from maingame.cpp in its update function. Now you'll also notice when you go to the the main game loop, which is the run function, you'll notice we're doing the fixed time step that we had in the zombie game. However, you'll notice I'm using uint32 here instead of a float. That was actually a bug we had before. It was working, but we weren't getting the maximum precision for getting the ticks, and that's something the warnings would help us notice, because the warnings were actually telling us we were using the wrong variable, but I was ignoring it, so sorry. And alright, so let's go real quick to ball controller so I can show you kind of how the update is working. So this loops through all the balls, and it will update their motion and gravity and all that as long as they're not grabbed. We have this one variable called mGrabbedBall, which is the index of the ball we are holding on to. If it's -1, then we are not holding on to a ball. If it's anything else, then it's just the index of the ball, because we store all the balls in a vector. And here we have these mouse motion events, on mouse down, on mouse up. Those handle grabbing the ball. You can look through the code. It's really simple to understand. We have this collision checking code here. This checks the collision between two balls. It uses some deflection code I got online. I didn't figure this out on my own, which is probably why there's a bug, so feel free to fix that and leave a comment. And yeah, we calculate gravity here. Yep, this is all pretty simple stuff that you guys should be able to understand, but if anything confuses you, do not hesitate to ask me in the comments, and I would be happy to elaborate on any of this code. So let's go ahead and talk about those macros I wanted to talk about. Let's go into main game, main game.cpp, where we initialize our balls, init balls, sounds dirty, and here is where we create all of the balls in the game. Now we have this variable up here at the top that is the number of balls we want to spawn. For now we're just doing 100. And then right here, this is where we set all the different types of balls. We have this possible balls vector that is a vector of structs, and here we have this ball spawn struct. This defines a spawn for a ball. So we can spawn a ball with a certain mass, radius, color, minimum speed, maximum speed, and a probability of spawning. Now this probability is just a relative probability. It takes all of the probabilities of all the balls and adds them together to kind of average the different probabilities to figure out what's going to happen. So if, for instance, this probability is 20 and this probability is 10, then you can expect 2 of these balls for every 1 of this ball. And the way this works is we need to keep track of the total probability so that we can use this uniform real distribution here to generate a number between 0 and that total probability. And then down here, for each ball that we want to spawn, we generate a random number between 0 and total probability, and then we loop through all the balls and check if that number is less than their probability. Now each time we add a ball, we set its probability to the total probability so far. So this probability of the first ball is going to be a 20, then the next one is going to be a 30, the next one is going to be 31, since we're adding 20, and then 10, and then 1. So what that means is we're going to generate a number between 0 and 31. If the number is anywhere between 0 and 20, we're going to take the first ball. If it's anywhere between 20 and 30, we'll take the second ball. If it's anywhere between 30 and 31, we take the third ball. So that's how this works. It's really simple. There's a little bit of code down here for getting a random position and a little hacky way to get a random direction. And then we finally add the ball to our mballs array with mplaceback. Now, I'm not using pointers to balls. I'm not allocating them with new because that'll make iteration a lot faster. It makes it a lot more cache friendly. However, if you want to later delete balls and swap balls around, you have to be wary because the ball controller is assuming that your ball struct or your ball array is never going to change with this mgrabbed ball integer. Just keep that in mind if you want to tweak this code a little bit. Alright, so let's go back to main game. And what we're going to be doing is improving this right here. This code is pretty ugly. We have to remember to add this probability every time. When people look at it, they don't really understand what's going on. We can do better than this. Now, what we could do is, instead of having 2 lines of code for each of these, we have 1 line of code, and we'll just have a function or something that's called like add ball. So we could say void add ball. Oops, add ball. We're not making a macro yet. And what we're going to need to do here is we're going to need to pass in all of these parameters here. So it's going to be a huge parameter list, kind of annoying. We're also going to want to pass in the probability, and we're going to want to pass in a reference to this possible balls vector here. And then what it's going to do is it's going to handle this for us. It's going to handle adding to the total probability and then putting total probability here so that we don't accidentally make a mistake later. However, there's actually an easier way to do that using a macro. The problem with doing it that way is I'm going to copy these and pretend we have all these parameters. I know this isn't how you actually declare parameters. If we later changed the ball constructor here that this uses, say we got rid of this parameter in the ball constructor, not only would we have to change it here, but we would have to change it up here as well. And we'd have to remember that, and if we don't remember that, we could have a bug, though the compiler will probably yell at us. There's a way to make it so that it will automatically change it there, and we only have to change it right here at the call site. And the way we can do that is with using a macro. So a macro you create with #define, and then we can define a macro. And you can use this to make variables, you can use this to make little inline function kind of things. And what this does is it's going to basically just expand the macro into some code. So I could say define we'll say print stuff, and then I could say std cout hello world, like that. And then I'll put a semicolon there. Now, what's going to happen is if I ever use print stuff, let's say I put print stuff right here, what the compiler is going to do is it's going to take this code right here and it's going to copy paste it right here whenever we're compiling. It's literally going to replace it. It's not going to be a function call or anything like that. It's actually going to put this code there. And you can do a lot of clever things with this. Now, it does make things harder to debug. As you can see, we have an error here. And it says error namespace SDT has no member cout. That's just because I need to include IOStream. But if you use a lot of macros everywhere, it can be a lot harder to debug your code. That's just one thing you need to be aware of. You should try to minimize your usage of macros unless you actually need them. So I'm not going to run it and prove it to you. You can do it yourself. This print stuff will print out hello world. You can do pretty much anything you want with a macro. You can put any kind of code in here and it's going to get expanded. We can also do functions. We can say print stuff with arguments here. And first we have to define an argument name. I'll put A. That's going to be our variable name. And then I can put A here. And now when I call print stuff, I can put parentheses here and put something there. I can say hello world. And hello world is going to be this A variable, and A is going to get placed right here. So it's essentially like calling a function, but it's not the same as a function because you got to remember the compiler is literally replacing this code. So if you do use it like this with functions, you have to be aware it's going to be hard to debug. Now, why am I teaching you this? Well, this is a way for us to make this part right here a lot simpler using what are called Variadic arguments. What we want to do is basically say take everything we put in here and use it in our little function call up here. So let's go ahead and make our proper macro that we want to use. We'll call it add ball. And a convention for macros is to always use caps. And for the arguments, let's do P for probability, and then comma, and now we basically want to say all of the arguments that are right here, everything. And what we can do is just put a dot, 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 and that's going to tell the compiler that we just want everything else that's inside the parentheses. And then on the for the actual definition of this macro, we're basically going to copy this. We're going to say total probability plus equals. And we're going to say, oops, we should not have that there. It should be here. We're going to say total probability plus equals, and we're going to say P. Now, if we want to go to a new line like this, this is no longer part of the macro. In order to actually put code on a new line after a macro, you have to put a / at the end. This indicates that you have another line that's in addition to this macro. Otherwise, the macro will end here. So we'll add the probability with that, and I'm actually going to do it like this. I think it makes it a little cleaner. And now we need to emplace back a ball, so we'll say possible balls dot emplace back. And then in here we want everything that they put in after the probability. And to do that, we just use a simple keyword va args, like that. And va args is going to be everything that is this dot, dot, dot. So everything that comes after P. And then we'll finally put a semicolon here. So now we can replace all of these with a simple call to add ball. For the first one, we'll do 20.0 for probability. And then what we're going to do is we're going to take all of this in here. And actually, yeah, we'll take all this and put it right here. And then we can delete this. And that makes it much simpler. And it's a lot less bug prone because now if we ever change the parameters for our constructor for ball, we can just, our constructor for ball spawn, we can just change the call site here and not have to worry about our macro. Now, could you use a function? Yes, you totally could. I just kind of wanted to show you this. So let's go ahead and do it for the other three, and we can finish this video up. So this one is 10.0f, and then we'll copy all of this. And the last one is 1.0f, add ball 1.0f, and I forgot a semicolon here. And we'll grab all this. Now you're noticing that the compiler is not yelling at me saying total probability doesn't exist and possible balls doesn't exist. That's because it doesn't actually need to exist here. We're just defining the macro here and it gets expanded down here. Whenever it's actually called, whenever we actually call add ball, total probability and possible balls do exist because they're defined right above where we call the macro. So adds the balls using a macro. Alright, so now let's run it and make sure it still works. We got some compiler warnings that I'll have to fix. And there we go, it's doing the same exact thing. So that's mostly it for this tutorial. I'm going to show you real quick why, oops, I forgot I got to drag this over. I'm going to show you why we are going to learn spatial partitioning real quick before we go into the next episode. Let's see what happens if we crank up the number of balls. Let's go to 1,000, and let's make the balls a lot smaller. Let's give them a radius of 2, 3, and 5 instead of 20, 30, and 50. Now let's run it and see what our frame rate is. So the balls are a lot smaller. We're still getting 60 frames per second though, because our sprite batch class is really efficient. The rendering is nice and efficient. And since we are not using new, whenever we iterate through all these balls, it's really, really quick and nice and cache friendly. But there's still a lot of collision checking going on. Every time two balls want to check collision, they do a good bit of code, and all of these balls are checking collision with every other ball every single frame. So if we have 1,000 balls, every single ball is checking with 999 other balls. So let's see if we can make it lag. Let's set this to 4,000. Rendering wise, we should easily be able to render 4,000 balls, easily. However, as you can see, we are now getting like 2 frames per second with 4,000 balls. We should easily be able to render these, but the problem is all of that checking, every single ball has to check 3,999 other balls, and that's just really slowing down the game. It's an exponential blow up. So in the next tutorial, we're going to figure out how to fix this so that we can handle tens of thousands of balls on the screen rather than just thousands or hundreds. Thanks for watching, guys. I'll catch you next time. Oh, and check the description for this code.